This is the explanation for the capillary filtration pre-lab that is due on April 13th. You should already have this filled out. Let's just go ahead and go over each question. Now, on the very first question, I asked you to please draw this label or draw this figure. It's figure 1518b. It's on page 499 of the book, and to include all the values. Now, for some reason, when I upload this PowerPoint into this program, it doesn't show all of this symbols. And the symbol for osmotic pressure looks like this. It kind of looks like the symbol for pi, but that represents osmotic pressure. So when we look at this figure, we're looking at a capillary bed. We have the flow of blood entering in this vessel, and then it's exiting to that vessel. At the very left end of this capillary bed is the arterial end, and then the right side of this vessel showing the capillary beds represents the capillary beds, the venular end. So as the blood goes in through on the left on the arterial end, it is full of oxygen and nutrients for the tissues, and then by the time the blood leaves through the venular end, it has dropped off the oxygen and nutrients and picked up cellular wastes and carbon dioxide. The blue arrow represents hydrostatic pressure, and it is showing what it's doing to the direction of the fluid. So at the arterial end, hydrostatic pressure starts at 32 millimeters of mercury, and then as it loses fluid, by the time it gets to the venular end, the pressure has been reduced to 15 millimeters of mercury. So let's look what's happening. That means the hydrostatic pressure is decreasing. It's higher at the arterial end, it's lower at the venular end, because it starts at 32 millimeters of mercury and it ends at 15 millimeters of mercury. And the red arrow represents osmotic pressure. And fluid flows towards a higher osmotic pressure because it wants to dilute the solutes. So let's look at osmotic pressure. It starts at the arterial end at 25 millimeters of mercury, and at the venular end it ends at 25 millimeters of mercury. So what does that tell you? That tells you that osmotic pressure doesn't change. Well, what creates osmotic pressure? That would be the albumin particles, the proteins that are in our cardiovascular system. It is creating the osmotic pressure, and the proteins should not be leaving the capillaries. They should stay inside of the blood, and that is because they're too large to leave through the intercellular clefts, and they're too large to leave through exocytosis. So the driving force of fluid at the arterial end is hydrostatic pressure. It is higher than osmotic pressure, 32 compared to 25. But when we get to the venular end, because hydrostatic pressure decreases as it goes through the capillary bed, osmotic pressure is the driving force when we get to the venular end, because it's higher than the hydrostatic pressure. So if anything affects the osmotic pressure, it affects the flow of the fluid, and anything that affects the hydrostatic pressure also affects the flow of the fluid. The second question on the pre-lab is, what is edema? Well, edema is the accumulation of fluid in the interstitial spaces, the fluid between the cells. And then I have little 2a. What are the two usual causes of edema? The two causes are inadequate, I can't really write this very well, inadequate drainage, which has to do with the lymphatic system. So inadequate lymph drainage causes edema. The other is having blood capillary filtration pressure that exceeds absorption. So that means the hydrostatic pressure is greater than the osmotic pressure, and that creates edema. Those are the usual causes: inadequate lymphatic drainage and hydrostatic pressure that is higher than the osmotic pressure. All right, the next question wants you to list 3 factors that disrupt the normal balance between capillary filtration and absorption, and then what causes each one. You can find this on page 500 of the textbook. First, when there's an increase in capillary hydrostatic pressure that could be caused by heart failure. Last week, we looked at a case study about heart failure, and it was left-sided heart failure where there was a mitral valve prolapse. and the blood was backing up in the pulmonary system and was decreasing in the systemic system. So it created a higher than normal pulmonary pressure and a lower than normal systemic pressure. So what would cause a higher than normal hydrostatic pressure? That would be the right-sided heart failure. So factor number 1 could be an increase in capillary hydrostatic pressure caused by caused by right-sided heart failure at the tricuspid valve. The second factor could be a decrease in the plasma protein concentration due to severe malnutrition or liver failure. So a decrease in protein concentration in the blood is going to decrease osmotic pressure. So a lower than normal osmotic pressure in this picture, it shows you it's at 25 millimeters of mercury. When in times of protein starvation, when there's not enough protein to make the albumin that is the main protein that creates the osmotic pressure, would lower that. So instead of being 25 millimeters, it would be lower, like maybe 20 millimeters of mercury or 15 millimeters of mercury, which would be really severe. But any type of change, anything that makes the osmotic pressure lower, is going to decrease how much fluid is going back into the capillary bed. And then a third factor, if there's an increase in the interstitial plasma proteins due to excessive leakage of small proteins from the capillaries. What does that mean? That means if there is some sort of leak in the capillary wall, and now proteins can leave the capillary bed. If the proteins leave the capillary bed, what's that going to do to the osmotic pressure of the interstitial fluid? It's going to increase the osmotic pressure of the tissue surrounding the capillary bed. And since fluids travel towards a higher osmotic pressure, it's going to retain the fluid in the interstitial spaces instead of returning it all back into the capillary bed. The next question asked, what is vasovagal syncope? You can find the answers on pages 478 and page 495 in the textbook. It's whenever there are signals from the nervous system that cause a sudden decrease in blood pressure, and then the individual will faint due to lack of oxygen to the brain. It can be due to emotional reactions or positional changes. So in other words, what's happening? The sympathetic nervous system kicks in, and whenever the sympathetic nervous system kicks in, it vasodilates blood vessels, especially in the lower limbs and in the upper limbs. When that happens, if the cardiovascular system is unable to, at that moment, to compensate, then the blood supply to the brain will be reduced. Reduced blood supply to the brain reduces the amount of oxygen that reaches the brain, and it causes fainting. Syncope, that means to pass out or to faint. Vasovagal has to do with the blood vessels and the vagus. The vagus is the cranial nerve number 10, and it goes to the blood vessels and it monitors your blood pressure. Now, if you stand up suddenly after lying down for long periods of time and your cardiovascular system cannot compensate quickly enough, the blood vessels will dilate in the lower limbs. The blood stays in the lower limbs more than it goes up to the brain, and it deprives the brain of oxygen, and it makes you pass out. So that's the concept behind vasovagal syncope. You can see something shocking. Some people pass out at the sight of blood, and that's what's happening. The blood vessels dilate to the limbs, and there's not enough oxygen getting to the brain. Let's see, good old Tom. Tom loves to soak in hot tubs and whirlpools. One day he decides to raise the temperature in his hot tub as high as it will go because Tom is slightly moronic. After a few minutes in the very warm water, he feels faint and passes out and nearly drowns. Luckily, he is saved by an observant bystander and explain what happened in detail. In this question, I just want to point out that he is saved by an observant bystander. Is that a fancy way of saying that it's a stalker? I don't know, because why else would somebody be observing him getting in his hot tub? Anyway, well, in response to the high temperature of the hot water, Tom's body is shunted more to the superficial veins to decrease the body temperature. That's how the body compensates for an increase in core temperature. It vasodilates the blood vessels on the surface to help bring the heat to the surface and cool the inner core temperature. With the superficial blood vessels being vasodilated, it will cause a decreased venous return. And because of the decreased venous return, that means the cardiac output is decreased. the cardiac output is decreased and the stroke volume is decreased, and it's going to lessen the amount of oxygen going to his brain. So with the decreased oxygen getting to his brain, it's causing him to feel lightheaded and faint. All right, number 6, how does protein starvation affect osmotic pressure? How does a high protein diet affect that? And then how would osmotic pressure of 30 millimeters of mercury affect the fluid flow across the capillary? All right, so a lot of questions, and I just went ahead and pulled this picture back up. So how does protein starvation affect the osmotic pressure? Well, if you're starving yourself for protein, then you're starving yourself of amino acids, and the liver needs amino acids to make albumin. It needs amino acids to make other proteins that are important for the body. So if you're starving yourself of proteins, then the liver has to get those amino acids from somewhere, so it's going to get the amino acids from the albumin that's already existing. So protein starvation would reduce or lower osmotic pressure. Now, how would a high protein diet affect osmotic pressure? Well, a high protein diet would increase the osmotic pressure. Now, this last question, how would osmotic pressure increase of 30 millimeters of mercury affect the fluid flow across the capillary? Normally, it's 25 millimeters of mercury. So if that increases to 30, and hydrostatic pressure starts at 32, and then before we even get to the venular end, osmotic pressure is going to be higher than the hydrostatic pressure. So that means your blood volume will increase, which will increase your blood pressure. And then the last question. Children who suffer from protein starvation have bloated bellies of ascites, which is an accumulation of abdominal fluid. How would a shortage of protein in the diet cause this condition? During protein starvation, the liver still needs amino acids in order to make the other proteins for the body. So one of the largest proteins, actually the largest protein in circulation, is albumin. So in absence of those amino acids in the diet, the liver will take the albumin, break it down for its amino acids, and use it to make other proteins. So if we reduce the amount of albumin that's in the cardiovascular system, that means we are reducing or lowering osmotic pressure in the capillary beds. So if we lower the osmotic pressure in the capillary beds, that means there's going to be an accumulation of fluid in spaces. And it just so happens that the vessels and the capillaries in the abdomen have a lot of space around them. So the fluid buildup will be more evident in the abdomen compared to the other areas like in the upper limbs. So that's why the fluid will build up in the abdomen compared to anywhere else. And the fluid is building up because there's a lower or a decreased amount of osmotic pressure in the capillary bed. All right, so that's the end of this pre-lab. The quiz over the capillary filtration will be on April 20th. All right, email me if you have any questions.